which is a talk by Mr. Maybe Chandu, Krishna, and Venkatesh. And the presentation will be about propeller blade load calculation for actuator disc using blade element methods. The floor is yours.
Yeah.
Go ahead.
Hello everyone. I hope you can hear me.
Yep, sounds good. Go ahead.
Yeah. Hi, I'm Y. Chandu Krishna, PhD student at CSIR National Aerospace Laboratories, Bangalore, India, and Dr. T. N. Venkatesh is my PhD supervisor. Today, I'm going to talk about the propeller load calculation for the actuator disc using blade element method. This is a part of my work. The motivation behind this work is the accurate simulation of interaction dominated flow fields is very challenging. For example, when we have a propeller at an angle of attack, and also when there are some structures upstream or downstream of the propeller, such as a wing or fuselage surrounding the propeller, and there are multiple propellers in the flow domain, the interactions and there will be mutual interactions between the propeller and the structures. And also here in the figures we can see the interaction dominated flow fields, where we have multiple propellers and there are structures downstream. And also there was a interest on prediction of installed thrust and power prediction for the propeller powered aircrafts in our group. And this is the motivation for our work. And you can see that there are different ways to model the propeller according to the required fidelity. We have blade element method and vertex lattice method, etc., as the lower order methods. And in the CFD methods, particularly in SU2, we have actuator disc technique and full blade modeling techniques, where in the actuator disc technique, under actuator disc technique, we have uniform load technique and variable load technique. And in the full blade modeling technique, we have a rotating reference frame simulation technique with or without periodic boundary conditions, based on whether it is an axisymmetric case or something. And there is a sliding mesh method where we can model a full propeller in a rotating zone and other stationary structures in a stationary zone, and such that it should resemble the actual flow field. And we have we see here that uniform load actuator disc technique requires the delta pressure across the disc, that is the prior information of thrust or delta pressure across the disc is required. And using this technique, we'll have only the axial induction, axial velocity jumps can be seen with this technique. And with the variable load actuator disc technique, we should have the prior information of the propeller blade loading along the radius. And using this technique, we can have the axial velocity jump and tangential velocity jump also. But we should have the propeller blade loading information in the prior. And the main focus on in this work is to combine the two different methods, like this blade element method and actuator disc technique, where the propeller load is calculated using the blade element method. And this technique is named as SU2 BEM. And this slide shows the brief methodology of blade element method. The blade element method is a methodology where we can get the thrust, torque, or power of the propeller with the given flow details, propeller geometry, and aerodynamic details of blade sections. And these are the equations which we are going to use to get the radial variation of thrust and torque. And the input details are as shown here. The left figure shows the radial is just some arbitrary data plotted on some arbitrary data. We should give the radial variation of chord and also the set blade angle to as an input at different radial sections. And also we should have the prior information. This figure on the right shows the propeller blade section at different radial stations. And we should have the prior information of alpha versus CL and CD for each airfoil in this section. and we have to give the data of this radial variation of chord and blade angle, and also this alpha CL and CD variation with alpha as an input to the blade element method, such that we can get the thrust and torque using these equations shown. And this is the flow of the technique SU2BM implemented. And if the user chooses to go with the blade element method, first it reads and stores the data given as an input to the solver. And as and when the solution proceeds, and at the actuator disk, at the actuator disk, we'll at each vertex on the actuator disk, the BM routine will be called, and using the BM routine, we'll get the radial variation of thrust and torque. And the BM routine uses the local flow solution to get the thrust and radial variation of thrust and torque at the on the actuator disk, and it is done at all points on the actuator disk. And this dt by dr and dp by dr is used to calculate the velocity jumps and pressure jumps at the outlet. And this is this process is continued, and this process is repeated again and again for every iteration, such that the blade loading gets updated every time pertaining to the local flow conditions, such that it should account the installation effects. And this procedure is continued till the convergence. uh, what are the features of SU2BM are, we don't need any prior information for propeller thrust, and also bookkeeping can be avoided. Bookkeeping of blade loading can be avoided for various thrusts and blade angles, because we should have we don't need to have the blade loading to be given as an input. And this is a two-way coupling technique, where the information between the propeller disk and the flow field is mutual, because the blade element method uses the local flow solution as an input. And each every time the propeller loading gets modified, and the modified propeller loading is used to calculate the velocity and pressure jumps at the outlet, and in such a way the slipstream flow is also gets modified. And we can get the it can predict the installed thrust and torque, and also we can see the rotation in slipstream using this method. And it accounts for installation effects, as it is taking the local flow solution as an input to this blade element method. And these to implement it into SU2, these are the changes made to the code. We can see that 5 extra routines were added to the C Euler solver class, and this read data is started reads the data which is given as an input before the start of iterations. And this gen AcDis data BM routine loops over all the vertices on the actuator disk, and it calls the BM model for every vertex. And the BM model takes the local flow solution as an input and calculates the thrust and the elemental thrust and torque at that point, and it sends back and it returns the value to the gen AcDis BM. BM model uses the interpolate CLCD data to get the intermediate to get the CLCD at intermediate alphas from the given input data. And in this routine we store the data of elemental thrust and torque at each point on the disk. And this BC AcDis BM routine takes the dt by dr and dp by dr to calculate the induced axial and tangential velocities at the disk at the outlet. And this BC AcDis BM routine uses the procedure of variable load actuator disk, which is already existing in SU2, to calculate the axial and tangential velocities at the disk. Basically, what we are doing is, instead of giving the already a known propeller blade loading to the SU2, we couple the BM model to calculate the blade loading according to the local flow solution. and this blade loading is given to the already existing variable load actuator disk procedure to calculate the axial and tangential velocities at the disk. Here the blade loading is updated every iteration, unlike the variable load actuator disk procedure, where the blade loading will be constant throughout the throughout the solution procedure. And these are the changes which are required to be made to the config file, and the text which is shown in blue should be added to the config file to access the blade element technique in SU2. Here the actuator disk type should be chosen as blade element, and we should give the RPM here at the actuator disk markers, and three new options were added, which is the actuator disk CG, which takes the center of the gravity center of the actuator disk, and the input, and it also takes the input file name which is given in config file, and also the set blade angle for the particular problem at 75% of the radius. A sample BM input file is shown here, which consists of this mm, details like number of blades, propeller diameter, and also the radial variation of chord set angle. And at each section, we have this alpha CLCD for the sections given here. And here because we are storing the values of dt by dr and dp by dr at each vertex, these values were integrated or integrated on the disk to get the overall thrust and torque and these thrust and torque is printed in the actual disk properties, which is already for every 40 iterations on the console. The text highlighted in blue is the new addition here, where it prints the integrated thrust and torque from BEM on the disk. And to validate this SU2 BEM, we have considered two different cases. One is the isolated propeller case, and the other is the wing with propeller case. The flow details and the geometry is shown here, and the test done is also described here. This slide shows the variation of thrust with the advanced ratio, thrust and power with the advanced ratio, and the experimental results are compared with the computed results from SU2 BM. We can see a good match at slightly at lower advanced ratios, and some mismatch is observed at the slightly higher advanced ratios in both thrust and power. The next case which is compared is for the same isolated propeller case. We compared the radial variation of coefficient of total pressure and non-dimensional tangential velocity along the radius. We can see a good match between the experimental and computational results along the radius, except very near to the nozzle. And this is how the convergence is observed. We can see in this plot is the density residual plot, where we can observe a similar convergence is observed for both SU2 BM and VLAD. And this is how the thrust and torque, computed thrust and torque converges. These oscillations are seen here because at the starting of the solution, we can see the local flow field solution varies at the disk. So according to the local flow field solution, the thrust and torque are calculated. So we can see some changes in thrust and torque in the initial flow solution. And as and when the solution is going towards the steady state, we can see the converged thrust and torque here. And this is the variation of thrust with angle of attack. We can see a similar trend is observed, like increasing trend is observed with angle of attack in both experimental and computed results. Here it could SU2BM could predict up to in almost all at all angles of attack. A slight mismatch is observed at slightly higher angles of attack. Next is the wing with propeller case. Here, this is the only wing case. And here, all the techniques, all the actuator techniques available in SU2, that is uniform load actuator technique termed as SAD here, and VLAD and BEM are compared. We can see because we don't have any rotation imparted in the SAD technique. We'll see. We don't see any lift change here. We can see an increase in lift, increase and decrease in lift with the use of VLAD and BEM. And BEM is is closer to the experimental results, as it takes the installation effects into account, because the propeller is there downstream of the propeller, because the wing is there downstream of the propeller. It accounts the variation, and a similar observation is made at angle of attack 4. This is the chord-wise variation of CP at different span-wise stations. Yeah, here the plots compare both in the regions which are outside the slipstream and inside the slipstream. These B and C are the cases which are inside the slipstream. We can see a good match between the experiments for SU2 BEM. And these are the CP contours, because in the SAD technique we could see a symmetry in the CP because no slipstream rotation is imparted. But here with VL8 and SU2 BM, because the slipstream rotation is there, we can see an asymmetry here. And the other works which I did using SU2 BM are the numerical analysis of wing with tip-mounted tractor and pusher propellers, and the use of vertical confinement technique with SU2 BM is examined. Coming to the conclusions, the SU2 BM technique is successfully implemented into the compressible solver of SU2 in version 7.1, and these are validated against experimental results. We observed a good convergence with the new technique, and it takes a slightly higher computational time than the uniform load and variable load actuator techniques. Maybe we can say like around 10% of higher computational time. And this is my work I want to do in continue. This I want to extend it to multiple propeller geometries, and implementation of this technique into the incompressible solver where free stream velocities should be examined. And thank you. This is my presentation. I'd be happy to answer any questions out there.
Yes, thank you very much.
Yes, sir.
So, any questions from the audience or online? Because of course, the question that is on everybody's lips is it in develop? Can we use it? Can you comment on this?
No, sir. It is not in developed, because it is developed for some R&D purposes in here in by our group, and we are planning it to make some modifications according to the code requirement by SU2, and we want to make it available to all.
Oh, that's great news. So we're looking forward to it.
Yeah. Yes, sir. Thank you.
So a question from the audience, Evert?
Thanks very much. Are you also planning to compare to the body to somewhat, because from like the work is that seems very similar.
Yeah. So the question is about can you use it with the body force model? Can you comment on it? Can you use it for the body force?
Body force model?
Yes, that's already in SU2.
No, we didn't try it on it. I think we can use it because it works for all, for everything. Yeah. Even for this, using the source terms, we could it could work. So I think it could work with the body force also.
Okay, so still some research to be done on that. Okay, yeah, thank you very much.
Yeah, thank you.
Let's thank the speaker again.